Oh, okay. All right, so we're recording now. Leanne, did you want to say what you were confused about? And then I can, or when we get there, maybe let me know, and then we can talk more about it. Okay, let's go ahead and get started. Are we all good to start? Leanne, did you want to ask me? Oh, okay, you're ready? Okay. All right, so we start things off with something we've already talked a little bit about. In fact, so hopefully that kind of made things a little bit easier in this section. And that is Hooke's law. So in physics, we like to talk about this thing called simple harmonic motion or simple harmonic oscillator. Okay. Now, an oscillator, and because there's going to be a lot of text on this one, let's try to switch the color up a bit here. An oscillator is anything with periodic motion. So, any object, and let's be even more specific than that. What does periodic motion mean, right? It's any object whose motion repeats. And we would even say that something whose motion approximately repeats, we would even call that an oscillator as well, because, you know, in reality things lose energy, right? If something loses energy, of course it's not going to be moving the same way forever, right? So any object whose motion repeats, we'll put in parentheses, even approximately. And then this part right here, the simple harmonic oscillator part. Now, the simple harmonic oscillator moves in a very specific way. In fact, a simple harmonic oscillator has a restoring force which is equal to minus kx. And this is, of course, Hooke's law that we've seen already. So if I can write down the force that acts on my oscillator in this form, where the force is proportional to the oscillator's displacement from equilibrium, then I would call that a simple harmonic oscillator. Okay, so that's the idea. We have something that repeats its motion, and if I can write down the force that acts on that object that causes it to repeat its motion as like a Hooke's law force, then I'd call that a simple harmonic oscillator. To get a picture to go along with this, we can imagine maybe, let's actually get two pictures. So, whoops, I drew the lines on the wrong side. Let's maybe imagine two pictures. We have like a wall here, a stationary wall with a spring on it. And that spring is attached to a mass. And this mass is going to be oscillating back and forth. So imagine that this mass is displaced from equilibrium. Let's actually just use the letter x. We won't write delta x. So the meaning of x here is the distance that the mass is away from equilibrium. We can even write that out too. So x is displacement from equilibrium. Displacement from equilibrium. And suppose I stretched this mass an amount x, right? I just take my hand and I grab it and I stretch it, and then I just let it go. Let's stay in the same color here. Then what would happen is, well, then this mass would start to move back towards equilibrium, right? The mass has a force on it. There's a force on it in this direction, right? And the displacement vector, so we could, let's make x blue, huh? Let's make x blue so that way we can draw this vector right here and we can still see it. Okay, so that's our displacement vector. And our force vector is always pointing in the opposite direction to our x vector. So what's going to happen here? The force is in the opposite direction. Of course, this thing wants to accelerate to the left. So if its velocity is 0 here, if I just grab this thing and I stretch it, right? If I just hold it there, it has no velocity. So then if I let it go, it has a force on it. So that force is going to bring it back towards equilibrium. So here it is at equilibrium. This is the same mass. This is the same system here. So what we're saying is an amount of time delta t has passed here now to get to this next state of motion, so to speak. And now we're right at the equilibrium position. So x is 0 here in this case. And the force is 0. Why is the force 0? Who can tell me why the force is 0? So why is the force 0 at equilibrium? You can put your answers in chat. I'd like to see everybody kind of give an answer. Why is the force at equilibrium 0? We have one answer in the form of a direct message. All the net forces cancel out. There's only one force here. No friction. There's no friction in this problem. Maybe I should have said that earlier. I kind of forgot. Sorry. No net forces. There's no acceleration. Okay, that's good. We're using our brains. We're getting warmed up. What about this expression right here, right? This expression right here tells us what the force is on the mass due to the spring, right? Now that I've pointed this formula out to you, without giving you the answer, what is the force at the equilibrium position? Zero, right? Because we're at x equals 0 at equilibrium. Right here, right? So if x is 0, we're at equilibrium, and the force is proportional to x. So if x is 0, the force is 0. Good. Here's the catch, though. Here's the catch. I haven't written down the velocity. What is the velocity going to be? In picture 2, what's the velocity going to be here for this mass? Is it going to be 0? Is it going to be to the left? Is it going to be to the right? Here's what we'll do. That's my question to you guys. What is the velocity? Put 1 in the chat if you think no velocity. 2 in the chat if you think it's to the left. 3 in the chat to the right. So remember, we've stretched the spring, we've let it go, it comes back to its equilibrium position. What's the velocity? Interesting, a lot of 1s. Now some 3s. Christine has changed to 2. Okay, how about this? Now that everybody's given an answer, okay? I want to put you guys in rooms. Try to convince your partner that your answer is correct. Let's see, I have to choose the rooms. I have to put everybody with different answers. So let's see here. How many students do we have? We have 7. We'll do 3 rooms. Okay. All right. I'm going to give you guys like 3 minutes to discuss it, okay? 3 minutes to discuss it. Try to convince the other person that your answer is correct. Oh, good. Perfect. Room 3 has somebody with answer 1, 2, and 3. The other 2 rooms have, let's see. Did I get it right? So in room 1, we have somebody with answer 3 and answer 1. In room 2, we have somebody with answer 2 and answer 1. Do you have mics or no? Okay, I see you're discussing in chat. I just want to come and check in on people. I'm not here to answer the question or anything. I'm going to go to the next room now.
Yeah.
Let it go, then like it's gonna go to the left. But then I think but then originally on the first picture he put that velocity as 0. So
0.
Yeah. Hi.
Just continue discussing.
But now I know I think it's 2 also.
So we agree on 2 then.
Yay.
Okay, so I think everybody's getting it now. Closing the rooms. Now we wait a minute for everyone to show up. Go ahead and reshare. Is that everybody? Check the rooms. All right, that's everybody. Okay, so everybody get ready to type your answer in chat again. 1, 2, or 3. Okay, 3, 2, 1, vote. Wow. Who hasn't voted? 2, 3, 4, 5, 6, 7. All right, that's everybody. Good. Everybody has the correct answer now. Good. We can do that again if you guys want on the next one. Okay, good. So we've stretched the spring, right? So if we let it go, it's going to move in the other direction, right? Good. So the velocity here is not 0. The velocity here is, well, we don't know what value it is. Maybe we can figure out what value it is later, okay? But it's definitely to the right, or excuse me, to the left, sorry. Let me use a different color than black as well. Now that I'm thinking about it, black is probably not a good color for here. A little bit too cluttered. So we'll do it like this. So the velocity is to the left there like that. Okay. Before we get to the value of the velocity, let's do a little bit of a recap. Well, actually, in this case, not a recap. Actually, let's do the recap first. We're on Hooke's law. We've talked about Hooke's law before. Let's do the recap first. So there's energy stored in a system like this. Let's say energy stored in the spring. Does anybody remember how to figure out the energy stored in a spring? Anybody remember kind of like the thought process on that? Anybody can speak up, or maybe you can say something in chat.
I was just gonna say, I think it's potential energy.
It's potential energy because it's stored. That's good. So I'm not going to leave you guys hanging. Think about that for a second. I'll give you the answer here, but the answer is not important, right? It's really kind of how do we get that answer that's kind of important there. Why does the spring store energy, right? That's the answer, 1/2 kx squared. So the amount of energy stored in the spring is going to be proportional to the square of its displacement. So the more you, like if I double the stretching, I quadruple the energy stored. Okay, but let me just give you a refresher how we get that actual answer there. So the way you get that answer is you remember that work equals minus the change in potential energy. If I exert a force, let me write like an equation. And then I'll also write it in words here, just because I think it's a good reminder. So it's work, which is a force exerted over a distance, right? Force acting on an object as the object is displaced. And then we could go a little bit further. It has to be displaced parallel to the force. Parallel or anti-parallel for in the opposite direction. Hopefully we remember that work can be positive or negative. Force acting on an object as the object is displaced. Parallel to the force. The force. Just a little refresher there on work. So work then is force times displacement, delta x. Okay, now I'm just getting crazy here. So let's maybe, let's just have the formula here because I don't want to use too many words here. So force times, I said displacement, it could be distance. Let's just use D here. Let's just use D. And we'll put the X in when we talk specifically about Hooke's law. So work is a force that's parallel to some displacement or a distance that's traveled there in a single direction. This thing right here, this work equals minus the change in potential energy. The best picture that I always think of when I think about, you know, doing work and storing potential energy is just kind of lifting a mass. So if I lift a mass up into the air, a distance h, I have to do work, right? I have to apply a force. This is my applied force. And that applied force has to at least be equal to mg, right? It has to at least be equal. If I don't lift with the force equal to the weight of the object, then I just can't lift it, right? I'm just not strong enough if I can't exert a force equal to the weight. So at least equal to, I don't know why I'm obsessing over writing a bunch of words right now. I don't know if maybe that's better for you guys, I don't know. But let me write the precise mathematical statement first. So the applied force has to be less than or equal to mg. So force is at least mg. And the potential energy here that's stored as you lift an object, well, look, it's the force times the distance. So it's mgh, right? So M, G, H. So the potential energy, or rather the change in potential energy, is equal to mgh. And you might be wondering where this minus sign went here. Let's address the minus sign quickly, just so we're clear on what happens with the minus sign. In order for me to lift the object, I have to exert a force less. Did I say, oh my God, I said less than. Sorry, guys. Greater than or equal to mg. I have to lift the mass with a force that's at least mg, its weight. I have to lift it up with more force or an equal force. But gravity always exerts the same force. It's always mg. And if I lift an object in the gravitational field, it gains gravitational potential energy. So the force that's going to do work to change the energy is the gravitational force when I let go. And so we always reference the potential energy to the field, the gravitational field that's already there. So I might exert a force larger than mg to lift this thing up, and if I did that, I would actually accelerate the object up. And that would require more energy from me, and that energy would be lost. It would be like energy that heats up my muscles, right? Some chemical energy, you know, I'd burn some calories or whatever. That would be energy lost. So all that extra energy from me applying a force bigger than mg, that would just be lost to my body heat. But the gravitational force is always the same, mg. And so the gravitational potential energy is always referenced to the gravitational force. So when so again, the minus sign, the gravitational force is pointing downward. So that's anti-parallel, not parallel. So the gravitational force is in the opposite direction as I lift the object. So that's where the extra minus sign comes from, so that the final answer is plus. Okay, so notice the change in potential energy. When I lift an object, it gains potential energy. So lift means gain potential energy. That's going to be important in a second for the stretching of the spring. So when we lift a mass, we gain potential energy, or that mass gains potential energy. Okay. The force that is exerted in the case of a spring is the restoring force. I stretch the spring, right? So here's a spring. Let me draw a spring. Let's actually not waste time drawing a new spring. Let's just grab one we already have, right? Here's one we already have. And then we can clean it up. That x equals 0 is fine. There we go, that's good. Oops. There we go. So if I stretch the spring, again, I have to apply a force to stretch the spring, but it's the spring's force that's always there. And it's always F equals minus kx. And so that's the force that we reference the potential energy to. So now, if I stretch this thing, let's stretch it this way. We can just do this in paint. Look at this. We can just take this and maybe like, okay, maybe that wasn't a good idea. Okay, maybe what we can do is we can get rid of this part and then draw that again. Okay, it's been stretched. It's been stretched roughly this much. You can draw in your notes a little bit better scale. Exaggerate the stretching a little bit. And this right here is x equals 0. This is a mass m. So we've stretched it a bit. Notice that I always reference the stretching with respect to the center of mass. So here's the center of mass right here. Same with h up here. Notice that h is always with respect to the center of mass. So here's the center. So when we stretch it a distance x, the force on it, if I just stretch it to that position, I'd have to exert a force which is at least kx, right, in the positive direction. And of course, the spring force on this thing, again, is in the negative direction. And it has magnitude minus kx. Same situation here as the gravitational field. The gravitational field is down, opposite to my applied force. And so the force minus kx, when it acts on this object over a displacement x, is going to give a positive change in potential energy. So stretching is a gain in potential energy. But wait, there's more. If I compress the spring, then I push the spring to the left. And if I compress it, the spring pushes me back to the right. And so even more than just stretching, compressing also is a gain in potential energy. Okay, so whether I stretch it or compress it, I gain potential energy. And the reason for that is because the force is always opposite to the displacement. So if I displace it to the right, the force is to the left. If I displace it to the left, the force is to the right. So no matter what I do to the spring, I always end up adding potential energy. Compress it, I add potential energy. Stretch it, I add potential energy. The only time there's no potential energy is when it's at equilibrium. But as you guys discussed earlier, when it's at equilibrium, it can have velocity. And when it has velocity, it's going to have kinetic energy, right? Okay, let's just quickly remind ourselves, how do we get the potential energy stored in the spring? Well, the work we can think of as area under the force versus displacement graph. Because the force here is proportional to x, we have to plot the force as a function of x. If we don't do that, then we won't get the right answer. Let's do it the way we did it in class before. We know the answer is going to be positive, so I will plot the force as k times x, positive, rather than plotting it as minus kx. If I plot it as minus kx, then we have to remember that there's a minus sign in this formula right here. So I could plot it as minus kx and I'll get the same answer. I just have to remember it's minus the change in potential energy. But I'm just going to plot it as positive kx here. So the force, which is positive kx versus x, looks like this. The slope of this line is k. It's a straight line. And the area under the curve is now what I will ask you to tell me, okay? So what is your thought process here on this? How do we figure out the area under this plot here? So this is the area I'm interested in. What shape is that area? How do we calculate the area of it? And so forth. You can go ahead and put your answers in the chat. We have one answer. Two answers. Those of you who've given an answer, why don't you type a little bit of an explanation as to why you have that answer, just while you're waiting for other people to kind of think through their answer. So Leanne, that's okay if you don't remember. At this stage here, we're calculating the area here. So how would you calculate the area? The first thing you need to do is identify the shape, right? So we have a straight line here. So I could probably draw this diagram better if I used the actual functions here. So here are my axes, and then here's a straight line, right? And then we want to, we want to get the, maybe I'll draw this first. Get the area like this. And then maybe I can do this. Good, I'm glad you figured it out. So I think we're waiting on maybe 2 more people, I think. I want to make sure everybody gets a chance here to figure it out. I think maybe we're waiting on 3 actually. So waiting on, just to call some people out here, waiting on Sammy, Ju, and has Evelyn given an answer? Yeah, we're also waiting on Evelyn.
I think we're waiting.
Say it again.
Since we're waiting for answers, I just wanted to, this might be a stupid question, but back to the concept where you said like in a spring, regardless of whether you're stretching or compressing, the potential energy is it's like a positive, a gain in potential energy. Is it only in the case of a spring? Or there are other systems that
Any simple harmonic oscillator. So any simple harmonic oscillator can the restoring force can be written in the same form of like something times the displacement with a minus sign in front. So it doesn't necessarily have to be a spring, but there are other systems where you'll have simple harmonic oscillations, and it would be the same, yeah.
Okay, thank you.
Okay, Sammy, what do you got for me? Are you there? Okay, let's go ahead and go through the thought process real quick. So since we do have a straight line here, I already kind of drew a secondary picture here. Since we have a straight line here, which is F equals KX, we have a triangle that we want to calculate the area under. So the triangle, if I drop down a perfectly vertical line here, like this, that forms a triangle. This would be a right angle here. Then we can look at the base of the triangle, which is X, and the height of the triangle, which is KX. Okay. So applying the area of a triangle formula, 1/2 base times height, we get 1/2 X times KX, and we arrive at 1/2 KX squared. So many of you wrote 1/2 FX, which is still the correct answer, right? But it's nice to kind of take that one step further and substitute in KX for F. So that's good. A lot of you are getting that. So 1/2 KX squared is the potential energy stored in the spring. Now, how would we relate that? Let me go ahead and grab again. I want to grab another one of these because we're going to draw a bunch of them if I don't. Whoops. And then I want to stretch this down so I have more space to work here. Let me try and leave the important stuff on there for a second. So here's our spring. It's displaced from equilibrium, but what we said was once we let it go, it's going to go towards the middle, and it's not going to have a force on it right in the middle. Right? There's not going to be a force here in the middle. So now it's at x equals 0. And it has a velocity, which I think I used this dark red color for that. So it has a velocity to the left. That's what you guys discussed. I'm going to give you something else here to work on here in a second. And then maybe we can do a discussion like that again. How do we figure out what that velocity is? How do we figure out what that velocity is? Can we come up with a formula for that velocity? I'll give you a couple parameters to set this problem up. So here's what I want to do. I want to formulate a question here for you guys. So what is the velocity of the object on the end of the spring at equilibrium position, at the equilibrium position, if it has been stretched a distance a from equilibrium and then released from rest. Okay, so let's add some punctuation to this. What is the velocity of the object on the end of the spring at the equilibrium position if it has been stretched a distance a from equilibrium and then released from rest. Okay, and I want to point something out. So I've said that the spring is stretched a distance a. So that means that the maximum stretching in the spring is a. Okay. We know that the velocity initial is equal to 0. But we know that the velocity final, which we're going to call this the final velocity here at equilibrium, is not 0. That's what we're looking for. Okay. So go ahead and think about this question individually first, and then maybe we'll do like a discussion again, like we did last time, except this time it'll involve a little bit of algebra as well. So can we come up with a formula for the final velocity? That's my question to you guys. Maybe first think about what is true about this problem just in general, for a problem with no friction, for example. So now that I've given you guys a couple minutes to kind of think about it, I want you to put, let me know in chat if you have an idea of what to do or if you have no idea what to do. So just put like yes if you know what you're doing, you kind of have an idea, and put no if you don't know what you're doing, you have no idea. Okay, so there's enough for me to kind of give one more hint here, and I think this is the hint that I think will get you there to where you want to be. And that is, it's kind of something I said earlier, but it was kind of in passing, so maybe a lot of people forgot. We just looked at how much potential energy was stored. 1/2 kx squared, right? What is the kinetic energy? This is the initial potential energy. What is the initial kinetic energy? What is the final potential energy? What is the final kinetic energy? And of course, energy must be conserved, right? The initial energy has to equal the final energy, so total energy. Okay? So we want to use energy conservation here. The energy remains constant in this problem. Does that help? So now you can let me know, yes, if now you know what to do, no if you're still unsure. Okay, go ahead, keep thinking about it. It's a good, this is a good kind of tie-in for a lot of different physics topics. Let me just check in one more time with you guys. So let me know, are we, who is confused? Is there anybody who needs some help? If you don't need help, just go ahead and keep working. trying to find the final velocity at equilibrium. Ju and Leanne, I'll message you directly. Yes, it's an analytical expression for the velocity. let me just do a check-in for kind of everyone. I'm still kind of messaging some people directly, so there's definitely people still working, but those of you who kind of knew what you were doing, if you have an answer, you can feel free to direct message that answer to me on Zoom, and I can tell you if you've got the correct answer, or if you're stuck on getting the answer, but you kind of have, you kind of feel like you know what you're doing. Okay, so now I've just got too many messages, so it's kind of hard for me to go through and message everyone. So I think it's a good time actually to go over the question kind of together. There are still some of you probably working towards the answer. That's good. You can feel free to keep working and not pay attention to me if you want. But I'm going to start going through the question now and kind of explain the thought process here on this. So there's no friction in this problem. And so energy is going to be conserved. We're not losing energy to anything. So, well, rather, I guess I should say the energy is going to remain constant in this system, the spring mass system here. So what that means is that the total energy that we have stored in the spring, plus its kinetic energy, which happens to be 0 because it's not moving, should be the same as its final energy, which we have defined to be when the spring reaches equilibrium. So this here is the initial energy the spring has when it's stretched. So initial energy when spring is stretched. And this here is the energy when the spring reaches equilibrium. Okay? Which right away, that tells you that just because this thing is not stretched anymore doesn't mean it doesn't have any energy, right? It has energy. It's just in the form of kinetic energy. So what we do is we ask ourselves, okay, what is the initial potential energy and what is the initial kinetic energy? So I'm kind of repeating some hints I already kind of gave, but let's go through it. Because the initial energy is the sum of these two things, right? It's potential energy initially plus the kinetic energy initially. So we need to identify these two quantities here. Well, potential energy initial, we've just kind of proven that it's 1/2 kx squared when the force is kx, right? It has magnitude kx. And kinetic energy is always, always, always 1/2 mv squared. So if you forgot that, maybe you weren't able to really make progress here. But you have to kind of remember that it's always 1/2 mv squared. It's the energy of motion. That's what kinetic energy is. And one way to kind of remember it is to remember that if you double the velocity, you quadruple the kinetic energy. Right? It's proportional to v squared. So the initial energy then is going to be the sum of these two. But if the potential energy in the spring, or excuse me, if the spring is stretched and released from rest, which is what's stated in the problem, so the spring has been released from rest, but it began stretched a distance a, well then that means that our potential energy here is 1/2 k a squared. Okay, 1/2 k a squared. And our kinetic energy is 1/2 m0 squared, because it starts from rest, right? Starts from rest means velocity is 0. And so the initial energy is 1/2 ka squared. What about the final? Well, energy final, again, just writing the steps out, is potential energy final plus kinetic energy final, right? And potential energy final is again 1/2 kx squared, and kinetic energy final is again 1/2 mv squared, right? The same way we calculate these things doesn't change. But now x is 0 at equilibrium, not the velocity. The velocity is not 0 at equilibrium because this spring we stretched it out, and when we let go it's going to zoom past equilibrium and actually compress the spring, and then it's going to compress the spring until it can't anymore, and then it's going to be pushed out by the spring. It's going to zoom past equilibrium again. It's going to oscillate back and forth. So x equals 0 at equilibrium, but the velocity there is not going to be 0. Okay, and maybe I should have subscripted these. So this is x initial, this is v initial, this is x final, and this is v final here. So probably I should have subscripted those. Okay, that means that this energy final then is going to be equal to 0 plus, oh well, I should just write it out, huh? 1/2 k 0 squared plus 1/2 m v final squared. And v final squared is what we're solving for. We don't know what that is, right? We don't have a numerical answer for that. We just know that the stretching or the compressing of the spring at equilibrium is 0. So what we have then so far, and let's maybe change colors here on this, is that the initial energy should be equal to the final energy, and the initial energy is 1/2 ka squared, and the final energy is 1/2 mv final squared. Okay, and so I can go about now calculating the final velocity. When I do that, I find that the final velocity is k, let's say final velocity squared is k over m times a squared, and then square root it. It's plus or minus, and actually the plus or minus here is very important. Square root K over M times A. Why is the plus or minus? Why is the plus or minus important? Well, I could have just as easily compressed the spring rather than stretching the spring. And had I compressed the spring, this would be a compression here. Had I compressed the spring, then the force on this mass would have been in this direction. And so when it reached equilibrium here, then it would have a velocity in this direction, right? Pointing to the right. And if I compress the spring by an amount A, then the magnitude of the velocity at equilibrium would be the same as if I stretched the spring by an amount A. So there is symmetry in this problem here. If I stretch it by an amount A and I release it, then it will return to equilibrium with a velocity minus square root of K over M times A, because it's moving to the left, right? So we take left to be negative. If I compressed it by an amount A, well, then it would be pushed to the right. And when it reaches equilibrium, it would be moving to the right with a velocity plus square root of K over M A. Okay, so a lot going on there for that little question there. So I hope that was helpful there. Does anybody have any questions? Let's actually put the arrow in a better spot here. Okay, so it could be to the left or right, depending on whether we stretch or compress the spring. Yeah, let me scroll up. Sorry about that. So let's see. Can you still read if I zoom out? Maybe I can zoom out like that. I can show the whole thing. Does that help? Now I would actually like to take a short break. I actually really have to use the restroom. So let's go ahead and take like a 5-minute break and then meet back here at, let's call it 7:04, just so that way we have, so the clock just changed. So we'll meet back here at 7:04, okay? So meet back at 7:04 p.m. And we'll pick things up from there. Okay, we're back. Everybody here? Give me a thumbs up if you're here. Okay. All right, we're going to do another question, okay? How should I phrase this? Yeah. How would you describe just two. So here's my question to you guys. We'll do it the same way as last time. So the question is, how would you describe the velocity v final here? Answer 1, this is the maximum velocity for this system. It will never go faster than it goes at equilibrium. Or 2, this is less than the maximum velocity. At some other point during the oscillation, it will have a velocity greater than this velocity here. So think about that individually for a minute and feel free to put those answers into chat as you come up with your answer. Okay, lot of ones. We do have a 2. Okay, so most people have the correct answer, which is 1 here. Let's understand why 1 is the correct answer, just real quick. If I stretch the spring and release it, once it reaches equilibrium, so here it's stretched an amount, let's say A, then it will head back towards equilibrium, which let's say is right. Let's maybe not draw it so exaggerated. So now equilibrium is here. This is x equals 0. It will have some velocity in this direction, v. And since it has velocity in that direction, it will begin to compress the spring, right? So let's look at for a second what happens when it just compresses the spring just a little bit. So now it's compressed the spring just a little bit. X equals a little bit here. Okay. If it's compressed the spring a little bit, then there's a little force on it, right? There's a force F, which is a small force. Because it's a little bit of displacement from equilibrium. Well, then what that means is that the velocity here will be a little bit less due to the small acceleration. So this velocity here, so this is the velocity that we called V final before. This velocity here is now a bit less because of the small, let's just go small, the small force that is opposite the velocity. Okay, does that make sense? So since this thing has velocity at equilibrium, as soon as it starts to move, it begins to compress the spring. Once it starts compressing the spring, it starts to lose kinetic energy and gain potential energy. Excuse me. So its velocity decreases a little bit as it compresses the spring. If we now reverse the thinking, if we start with a spring which is compressed, we've already seen in the mathematics that compressing a spring or stretching a spring adds the same amount of potential energy. So when the compressed spring returns the mass to equilibrium, then that mass will have the same velocity, but in the opposite direction. And so when the velocity carries the mass away from equilibrium, stretching the spring a little bit, then again, it will lose some kinetic energy and gain some potential energy. It will lose a little bit of velocity as it is displaced from equilibrium. Okay? So the answer there on that one was 1. Maybe I should have put a check mark or like circle it instead of putting an X. That's the correct answer there. So it is in fact the maximum velocity. It's not some intermediate value. What would the minimum velocity be? Well, the minimum velocity, if we're talking about magnitudes, maybe, let's think about the speed. Really, I'm doing a bad job right now. I should really say the maximum speed, not the maximum velocity. I should say maximum speed. So it's the maximum speed. What would be the minimum speed? Well, the minimum speed would be when this thing isn't moving at all, right? The minimum speed anything can have is 0. You can't have negative speeds, right? So I guess technically the velocity at equilibrium is either the minimum velocity if it's the most negative, or it's the maximum velocity if it's the most positive. Okay, so just to really clarify on that there. So this really is the maximum speed at equilibrium. Does anybody have any questions about that? The next thing that we're going to talk about is period and frequency. Oh, what happened here? There we go. So period and frequency of periodic motion. Periodic motion simply means motion that repeats. Period is how long it takes for one repetition Of course, this is a time. How long it takes is a time, right? So it would be measured in seconds. And then frequency here is how many repetitions occur in 1 second. Okay. So as an example, if I have a spring which is compressed, and then it reaches equilibrium, and then it's stretched, and then it comes back to equilibrium, and then it becomes compressed again. I should say x equals minus a here. I really have to eyeball this here. Not necessarily to scale, okay? Not necessarily to scale. So it's compressed, and then it's at equilibrium, and then it's stretched, and then it's at equilibrium again, and then it's compressed again, and this is one period. The time that it takes for this to occur is one period. So let's say if this process takes 10 seconds, then the period is 10 seconds. Okay? So if this process of, if I compress it and I let it go, it goes to equilibrium and then continues to stretch. And then when it's fully stretched, then it comes back towards equilibrium. And then from equilibrium, it begins to compress again. And then when it's compressed back to its original position again, its starting position, that's one period. So the period is 10 seconds. I don't know if I can drag this down anymore. No, I can't. So I'll have to go to the side. Okay. You guys another like 10 seconds to finish copying that down. Okay, let's move forward. The symbol that we use for period is capital T. Okay, so in our last example, capital T would be equal to 10 seconds. Frequency, or F, is simply 1 over the period. It's the number of repetitions per second. So if it takes 10 seconds for one repetition, then only 1/10 of a repetition would occur in 1 second, right? Okay. So 0.1 inverse seconds. And we have a name for inverse seconds. We call it hertz. Capital H-Z, hertz, which is the units of frequency.
And the period is always in seconds, or it's just like recommended to be in seconds?
Well, it can be in units of time. For example, like the period of the Earth's rotation is 1 day, right? So I could convert that to seconds if I want it to be in seconds. We're going to focus on SI units in this class, right? So we want to put it in seconds just so that way we don't have to worry about, oh, are these units going to cancel or not, right? So we want to just have everything in the same units so that they cancel. But obviously you can have like the period of the Earth's orbit around the sun is 1 year, right? By definition. So yeah, you can have different units, but they're all units of time. It's the time that it takes for one repetition.
Thank you.
Mm-hmm. So if we have a spring system that we release from rest, we can show that the period, yeah, okay, this is what I want here. So we can show, if we write down for a spring, so for a spring, if we write down the energy of the spring, its initial energy, we saw that the initial energy, of course, has to be 1/2 Ka squared, right? Here's a spring. I stretch the spring an amount A from equilibrium. That's the furthest the spring is ever going to be from equilibrium, right? If I stretch it a distance A and I let it go and I don't touch it, then it will only ever be compressed in amount A or stretched in amount A, and it can be anywhere in between, right? Let's look at anywhere in between. We looked specifically at stretching it, letting it go, and letting it come back to equilibrium. Well, if we just look at some arbitrary time, so now we say energy final is somewhere I should just say some point in the motion of the system not necessarily equilibrium, but it could be equilibrium if we want it to be. Well, if we're looking at some point between the max stretch and just the whole motion of the spring, essentially, then it's going to have kinetic and potential energy. So it's going to have 1/2 m v squared plus 1/2 kx squared. And we don't necessarily know what x and v are. This is the energy of the spring somewhere in its oscillation, somewhere in that motion of the spring. So the spring is going to continue to oscillate back and forth. And we just want to look kind of in general at what's going on for this motion. So the only thing that we know about the system is that we've stretched it in amount A and then we've just let it do its thing. Okay. I don't want to go through a lot of algebra here on this part, so I want to cut to the chase. If we set energy initial equal to energy final, what we have is 1/2 Ka squared is equal to 1/2 m v squared plus 1/2 kx squared. What we can do is we can actually solve this equation for v. The solution for this equation for v is given by k over m times a squared, and I've factored in a squared out, so a squared is going to show up in the denominator here, times 1 minus x squared over a squared. I encourage you to go and run through this algebra. Oh, sorry, I forgot, this is squared here. I encourage you to run through the algebra yourself and show that this is true. And then take a square root on both sides. So the velocity of this thing at any point during its motion is given by this expression. Again, the plus and minus is actually really important here because the mass could be moving to the left or to the right. There's two possibilities at every point, right? It could be stretching the spring or compressing the spring, right? or it could be unstretching and it could be decompressing. So there's two possibilities at every point. So the plus or minus is really important here. And then times 1 minus x squared over a squared, but under a square root, right? Okay. So give me a thumbs up if you're with me here at this stage. I can't see thumbs up, so there we go. Okay. Give me a thumbs up if you're with me at this stage here. I'll give you some more time to copy that down if you need to copy that down. Okay, maybe a couple people need some time here. Okay, so let's go ahead and now show, I want to show something here. This is what I want to show. So let me present the answer first and then kind of show where it comes from here. What I want to show is that the period of this motion is 2 pi square root of m over k. Okay, so that's my goal here. This is my goal, to show that the period of this spring system is 2 pi square root m over k. You can check that that actually has units of seconds. The units of the spring constant are newtons per meter. So this is SI units, newtons per meter. And a newton is a kilogram meter per second squared. Kilogram meter per second squared. So kilogram meter per second squared divided by meters. Cancel meters, boom, boom. And then here there's a mass, right? So the mass is going to cancel, the kilograms here for the mass is going to cancel with the kilograms there. And we're going to end up dividing by 1 over second squared. That's going to flip up and multiply, right? And we're going to take the square root of it and we're going to get seconds. So this thing has units of seconds, right? So it has units of seconds. As it should, right? In order to show that this formula is indeed the correct formula, we should consider a system which is not moving along a straight line, but is actually moving in a circle. And let me use the circle draw feature here. But one which is identical to the spring system. Okay, so we have two systems here. One like this and one like that. And here we have this distance here is the radius of the circle. In other words, it is the amplitude, or A, the total stretching of the spring. That's why we use the letter A. I don't know if I mentioned that. We use A for the maximum stretching because A is amplitude. So when the spring is stretched to its maximum amount, A, and released, then it's going to move, let's say, to the left here if we begin on this side. If we begin on this side, this thing is going to start to move in this direction, right? Well, if it moves in that direction, then we should have a system here which kind of moves to the left as well. Look, so we've moved to the left here by an amount given by the path on this circle here. Well, we should make the velocity the same as well, right? So I use this color for velocity. If these two systems are going to be equivalent, then the velocity here should be the same, right? So that v should be the same as perhaps this v over here. Whoops. So we should make the velocity over here. If we're now at this stage here, the velocity should be the same here. It should be the same v. Okay, and this distance right here from this point to this point here should be the same. So this should be the same, or rather it should be actually this distance here. That should be the same. So that should be the distance x there. This distance here would be a minus x. So this right here, this distance right here from here to here is x. This distance right here would be a minus x. Okay. Well, if we do that, what we can show is that this height right here, in this triangle right here, let's actually draw it to the side. So this triangle right here, the side of this triangle is a squared minus x squared. In other words, it's a square root of 1 minus x squared over a. Where does that come from? Well, let's see where it comes from. The hypotenuse of the circle triangle here, the triangle in the circle, is a, right? Because the radius of the circle is a, so the distance to this point is a, and therefore the distance to this point up here is a, right? So from the center to that point on the circle, that's the distance a. The horizontal side of the triangle, this side right here, is just x. That's what we've called x up here in blue. That's x. So this is x, and this is a. So we can use Pythagorean theorem, right, to solve for this side here. So a squared equals x squared plus this unknown side squared, right? This unknown side squared, we don't know what it is. Well, we can solve for it, right? So it's going to be a squared minus x squared equals this thing squared. And I take a square root on both sides, right? So this unknown side, the unknown side here is square root of a squared minus x squared, right? So things are starting to look awfully familiar to me. I don't know about you guys, but didn't we just say that the velocity at any point, was square root of k over m a times the square root of 1 minus x squared over a squared? Didn't we just say that? And look, a squared minus x squared is the same as a, right, times the square root of 1 minus x squared over a squared. So these things are matching up. So indeed, we have a spring system here. I need to close my chat so I can see better. We have a spring system here which matches up with this circular motion that we have over here. So we've drawn an analogy between the oscillating mass spring system to a circular motion. Well, what do we know about circular motion? Well, I know that the time it takes to go around the circle one time, the time that it takes to go around the circle one time is the distance around the circle, which is 2 pi r, right? Divided by the speed that you go around the circle, right? Provided the speed is constant. Okay, what's the speed that we go around the circle here? I don't know what the speed is. I just know that the speed here in our spring mass system changes, right? Here's our spring mass system. The velocity changes. Here it is right here. It depends on where you are. It depends on x. Depends on x. But if we look carefully here, we can see that the x component of this circular motion is the same as the x component over here in the spring mass system. That was something we made true. We built the problem that way. But what we can show is that actually the velocity along the circle here, tangent to the circle, v max, is actually the same. It's always the same, okay? And the way we can show that is the following here. V max, I'm really running out of space, but I keep like having to scroll up and everything. So let me give you guys some time to copy that down. So to copy that down, you can say something in chat when you're good to move here. You can just put like 1 in the chat when you're done kind of copying anything. If I scrolled up too quick and you still need to copy something down there, let me know too. Also, let me know if there are any questions up to this point. I know it's kind of a weird analogy we're drawing here between the spring mass system and circular motion. Are we good to move forward? Nobody said anything in chat yet. Give me a thumbs up if we're good to move forward. Okay, yeah, so let's go ahead and move forward then. So the thing that we need to recognize now is that when we reach the apex of the circle up here at the top, when we reach this position right here, that corresponds to when we're at equilibrium for the spring system. When we hit equilibrium for the spring system, we will be traveling with the max velocity, right? And the max velocity will be square root, and I should say speed here. The max speed will be square root of k over m times a, the max stretching of the spring. And so from this uniform circular motion perspective, then that means we should have a velocity here, and I should have been using the maroon color for the velocity here. Sorry about that. So this is the velocity, the speed rather, the maximum speed here. So V max is square root of k over m a. And then we can recognize that when I have the point over here, when I'm looking at the point over here, If I know V max up here at the top is this value square root K over MA, then I can imagine for the circle here that the velocity here is the same. It's the same V max, but if I project V max onto the x-axis, in other words, take the x component, if I take the x component of V max, I see that it's indeed the same as the function that we got earlier. V equals V max square root of 1 minus, is it a squared? No, we can write it this way. No, this is actually the way we need to write it. X squared over a squared in the square root here, okay? Now the reason for that is because the angle at the top of this triangle here, let me see what, okay, we'll use green here. Okay, first I need to do this though. So let's put this out. Okay, we have green here. We have to use a little bit of geometry, which I'm going to skip over, but maybe you should take a look at it to prove it. It shouldn't be too difficult. That these two angles are the same. Okay, that those two angles are the same. So if that's true, which check that for yourself, if we scroll back up here, we saw that the tall side of the triangle, the height of the triangle, was a times square root of 1 minus x squared over a, right? So that's the tall side. So if I calculate the sine of this angle right here, I should put it in green. If I calculate the sine of theta, the sine of theta is going to be equal to opposite over hypotenuse. So a square root 1 minus x squared over a squared. This should be an a squared right here, by the way. That should be an a squared. Divided by the hypotenuse, which is a. So these cancel. A's cancel. So the sine of theta is 1 minus x squared over a squared. So we come over here and we say, okay, if that's theta right there, if this is theta right here, this is theta, then V max sine of theta is this component right here. So the x component, which is the same velocity that we have in our spring mass system, that's V max times sine theta. So that means that this right here is correct. So V max, this is the sine theta piece. Complicated, I know, a lot of algebra going on there. What do we need this for? Why did we go through this? Well, remember, we want to calculate this. We want to calculate the period of this spring mass motion, right? So in order to do that, we have to show that the spring mass system is equivalent to a uniform circular motion, where the uniform circular motion speed is the same as the maximum speed for the spring mass system. And it turns out everything is lining up. All our equations, excuse me, all of our equations are lining up really nicely. So we're going to be able to calculate the period now. So the period is 2 pi times the radius of the circle, which is a in our case, right? And then we have to divide that by V max. Why V max? Well, because we go around the circle with a velocity or a speed V max, right? So the total distance we go around the circle is 2 pi times the radius, or 2 pi a. And the speed that we go around the circle is V max. Okay, so here we go. 2 pi a. V max is square root of k over m times a. Boom, a's cancel. There it is. And then the fraction in the denominator flips up and multiplies. So here's the formula I promised you. 2 pi times the mass over the spring constant, K. So there's the period. So let's walk through the steps again, right? The reasoning matters here. So the first thing we did, we want to calculate the period of oscillation. So the time it takes for one repetition. So if we compress it and let it go until it's fully stretched, and then it comes back and compresses again, that would be 1 period. The time it takes for that, in order to calculate it, we had to draw an analogy between the spring mass system and uniform circular motion. Okay, and so all we had to do really was match the max velocity, the velocity at equilibrium for the spring mass system, to the speed in the uniform circular motion. And once we did that, everything kind of just fell into our lap. So if we knew that fact ahead of time, we could have skipped a lot of this algebra, obviously, right? But of course, we got to show that that's true, right? It's important to show that that's true. Now that we have this, we can see that there's one really important thing that happened here. And it's actually, it should surprise you. And that's this right here. The amplitude, the amount of stretching. A is the amount of maximum stretch or compress. Compression, stretching or compressing, right? The maximum amount of stretching and compression does not show up in our final answer for the period of oscillation. Let's write it in words because it really is that important. Let's write it again. The maximum stretching or compressing does not, stretching or compression does not show up in the final answer. Let's just say does not show up in the equation for the period of oscillation. You would think intuitively, if I stretch the spring more, that it would take longer for one period, right? Think about that for a second. If I stretch the spring more, then it has to go further back and forth, right? If I stretch the spring more, it has to go further. Its distance away from equilibrium is twice as much. Or sorry, is more. It has to go twice that distance, right? So, oh, whoops, click off of that and then scroll down. So the total distance traveled by the mass on the spring how much is it? If I stretch the spring in amount A, this is a good question for you guys to think about. This is a good question for you guys to think about. What is the total distance traveled by the mass on the spring? You put it as a question. So what is ... total distance traveled by the mass on the spring in one period or one repetition. So think about that. How much distance is traveled by the mass on the spring if it goes through one repetition? So it's stretched out A, and it goes all the way until it gets compressed, and then it goes all the way back until it's stretched again. How much distance? Anybody have an answer yet? You can put your answers in the chat if you get an answer.
Can you actually repeat what you said when you were explaining the question?
What is the total distance traveled by the mass on the spring in one repetition? So if I stretch the spring and I let it go, it has to go until it gets compressed, and then it has to go until it gets stretched again. So what is that distance that it travels? Does that make sense?
Is it like 4 times A?
Well, if that's your answer, put that in the chat.
Okay.
I don't see anybody else putting any answers in chat, so I'm wondering, do we understand what we're asking here? So now we're starting to see some answers here. Still waiting on a couple people here, so continue to think about your answer and maybe you'll change your mind. Really try to reason it out, right? Really try to break it down and see how much distance this thing actually travels. Break the motion down into sections. Okay, now I'm going to call on students who have not given an answer. So just starting with, let's see, we have Christine has given an answer, Kevin's given an answer, Sammy, Liliana, Denalise, Leanne. Ju has given an answer. Okay, Evelyn, have you I don't think you've given an answer. And yeah, Ju gave an answer. That's good. So Evelyn, I think we're only waiting on you. So now the spotlight's on you because you haven't answered yet. What are your thoughts here on this one? Maybe she stepped away for a second. Okay, so here's what I'll do. I'll let you guys discuss it again. I'm gonna put you guys into rooms again, and I'll give you 3 minutes to figure out. Try to convince the other person of your answer. Again, I will try to make it so that people with different answers are in different groups here. So let's see here. Okay, so I'm opening up the rooms. So I'll give you about 3 minutes. Oh, there we go. Yeah, sorry about that. Okay, if you're watching the video, then you can try this yourself. If you didn't come to class, the total distance traveled by the mass on the string in one repetition. I will turn off my mic and video, and I'm actually going to pause the recording this time. I want to try and hear what students are saying without kind of disrupting the conversation, and I think when I join in and it says recording in progress, it kind of interrupts. So that's what I'm going to do now. Okay, so I did pause the recording and it seemed like maybe it worked a little bit. I think it's less disruptive if I join the breakout rooms that way. So it seemed like it worked because I caught a few students like actually talking, which is good. I'll go ahead and close the rooms now. I think it's been about 3 minutes. Waiting on 2. Okay, waiting on 1. Okay, we're all here. All right. Go ahead and type your answers into the chat. I'll go ahead and share my screen again. So type your answers into the chat. Is that everyone? I think that's everyone. And that's good. The answer is 4A. I'll just quickly show that now. So here's equilibrium. This is x equals A, and this is x equals minus A. If we begin here, we must go a distance 2A and back another distance 2A. So the total distance is 4A. Okay. So if the total distance traveled by the mass on the spring in one repetition is 4A, then where was I going with this question? I kind of interrupted my own flow there. So we found the period. Oh, right. The period does not have the amplitude inside the expression, but you would think if the distance traveled depends on the amplitude, it's 4 times the maximum stretching A, which I keep calling the amplitude. You would expect that if I increased A, I would increase the amount of distance that the spring has to travel, right? And that would increase the time that it takes for the mass spring system to repeat, right? Its motion. But that's not the case. So what that tells us is that when we have an undamped spring, in other words, a mass spring system with no friction, the time that it takes for it to repeat its motion is the same no matter how much I stretch the spring. So let's just kind of pictorially show that. So if I have a spring and I stretch it this much, well, maybe not that much because then it wouldn't be able to compress. If I stretched it that much, the period would be the same as if I stretched it only this much. So I've doubled the stretching. This is only 1/2 A. I've doubled the stretching, but the period is the same. It's the same period. Same period, different stretching. Go ahead and copy those diagrams down. We mentioned previously that the frequency was simply 1 over the period. So the period is the time it takes for one repetition. So 1 over the period is the number of repetitions in 1 second. This quantity would then be 1 over 2 pi square root of k over m. Now, frequency has units of hertz, as we mentioned before. But in the direction that we're headed in a second here, it's nice to actually talk about what we call angular frequency, which is simply omega, which is 2 pi times the frequency. So you can think of omega as kind of, oh, we already talked about this. What am I saying? We talked about angular frequency already when we were discussing, what was it?
Like centripetal forces and stuff.
Yeah, all the way back to centripetal motion, but I think we discussed it recently too, but maybe even I'm forgetting, so I should just kind of cover it again. But the angular frequency is basically like if you have the number of repetitions as the frequency, then the frequency would be like the number of times that you go around a circle. So it would be like revolutions. Oh yeah, I guess that is kind of. So it's like the frequency is like the revolutions per second, and the angular frequency is the amount of angle theta that you go around per second. So this here, for circular motion, is the amount of angle theta per second. But there's no clear physical description of omega when you don't have a circular motion like that. So we just call omega the angular frequency and simply just multiply the frequency, which is the real physical thing, by 2 pi. That's what we do because it simplifies formulas. So we can actually write down a description of an oscillating mass spring system, as you might have already suspected. It's stretched, then it's at 0, then it's at A, it's at 0, it's at minus A, then it's at 0, then it's at A, then it's at 0, then it's at minus A, then it's at 0, then it's at plus A again. That's a sine or a cosine, right? So we write the position. We write the position as a function of time, x of t, as a cosine omega t. Or just as true, just as correct here, a cosine, and we can put the 2 pi in there, 2 pi f times t. But usually we just write omega because it's nice and neat, right? We just take that 2 pi f and we just put it into one symbol, omega. We could even take this one step further. We could say, okay, frequency is 1 over period, so we could say a cosine of 2 pi over capital T, and then times the lowercase t. The lowercase t is the variable here, right? The lowercase t is the variable. The big T is the period. That doesn't change. The big T is the period that remains constant for the entire motion. Okay. So of course the plot of this thing, if we were to plot x of t versus t, we begin at A, go to minus A, back to A, minus A again, and so on. So this is A, and this is minus A. And if you remember about sines and cosines, one repetition here, boom, there it is. That's one period. That's one period. To find the period, you have to look at this equation here, omega, the one with omega, because this thing is going to repeat every time it reaches 2 pi, right? So cosine at 0 is 1, and then when we get to cosine of 2 pi, it's going to be plus 1 again, and then cosine of 4 pi, it's going to be plus 1 again. So every 2 pi is the repetition. So when omega times capital T, so when T equals capital T, then this should be equal to 2 pi, right? And indeed, we can see that this is the case here because, okay, first off, don't plug in omega as 2 pi f or 2 pi over t. You don't get anywhere if you do that. You just get t equals 1 over f, okay? The thing to do here is to say, let's just divide both sides by omega. So t is 2 pi over omega, okay? And that's kind of a nice little formula because a lot of times, like for example, in circular motion, you know, it's just you have the angular velocity, which happens to be the same as the angular frequency for uniform circular motion. That's not the case for like our spring mass system. There's no angular velocity, right? Because nothing is rotating. There's just an angular frequency. So this value right here of 1t is 2 pi over omega. If you want to get all of the 1 periods, like if you want n, like the nth period, you could figure that out by just putting an n in the expression, right? So omega t equals 2 pi n, and you'll get that answer. So you just have an n up on the top. Questions about that? How would we find the velocity? Question for you guys. How would we get the velocity? If we do delta x over delta t, is that going to work? If I do delta x over delta t, is that going to work? Yes or no? 1 in the chat for yes, 2 in the chat for no. Should I do delta x over t? Should I do delta x over t? Those of you who are in the calculus class, should I do time derivative of x with respect to t? You can put 3 for yes and 4 for no. So if you're in the 205 class, this is your question here up top. If you're in 210, this is your question at the bottom. Well, a lot of you are in the calculus class all of a sudden. Okay. Well, that's good. So those of you who answered 2, you're correct. Delta x over delta t will not work. But I'm actually quite surprised that those of you who are in the calculus class are answering 4. Dx by dt will always work. You will never use dx dt and get the wrong answer unless you incorrectly calculate the derivative. Okay, so if you have x of t and you take the derivative with respect to t, you will always get the velocity. So that is your problem now. So if you're in 210, take the derivative of x of t. Okay. If you are in 205, pay attention to what I am going to show on the board now. Okay. Those of you who are in 210, you can look at the board, you know, after a couple minutes after you calculate the derivative. So here's what I'm going to do. Here's what I'm going to do if I'm a 205 student. I'm going to say, hey, wait a second. We already calculated the velocity in terms of x. Here's the velocity in terms of x. Aha! I don't need calculus. I simply plug in what x is. Right? This is how, this is how people did physics back in the day, before Newton came along and revolutionized, physics and math by inventing calculus. So now I need my trig students to tell me what to do when I have square root of 1 minus cosine squared. What am I supposed to do now? I haven't taken trig in, probably over 10 years. So I need you guys to remind me. What am I supposed to do when I have something like this? What am I supposed to do? I have no idea. I have 1 minus cosine squared omega t. I have no clue what to do with this. Kevin thinks he's in 205. Are you? Wait a minute. No, you are in 205, aren't you? No, you're not in 205. You're a chemistry major. You need calculus. No, see, you think you're in 205, but you're not. I'm only asking 205 students. I wish I could delete your message, but I can't. Spam your message away. 205 students, what am I supposed to do? What am I supposed to do? I have 1 minus cosine squared of something. Evelyn, are you in 205?
Yes.
I can't remember. Okay, so finally we have a 205 student. All right, good. So if I have 1 minus cosine squared, then I should get sine squared because I'm a diligent trig student, and I know that sine squared x plus cosine squared x equals 1 because I've mastered the unit circle, right? And the unit circle has radius r equals 1, and it has, at some point on the circle, the x coordinate of that point is cosine of theta, right? Here's theta. and the y component is sine theta. I guess I should have done a better job. Let's put thetas here. So sine squared theta plus cosine squared theta equals 1. So x coordinate is cosine theta, y coordinate is sine theta. So if I do Pythagorean theorem, right, I get cosine squared plus sine squared equals 1. So this term right here, if I treat omega t as theta, will give me sine squared. So treat this term as theta. Will give me sine squared theta. Oh, whoops. Well, theta is omega t, so let's put that down there. Omega t. And if I take the square root, I always have to be careful about plus or minus. Oops, I totally forgot my plus or minus here. I should have plus or minus, right? Because it could be going to the left or the right. It could be going to the left or the right. At any single point during the motion, it could be moving right or it could be moving left. And actually the magnitude of that number is the same. Doesn't matter what direction. But the sign does matter. So we get plus or minus V max sine omega t. And if I start by stretching the spring and letting go, if I stretch it in the positive x direction in amount plus a, and I let it go, it will actually head towards negative values of x. So I actually need to choose the minus sign. Look at that. I actually need to choose the minus sign for my answer. How often does that happen in a math class where the teacher says, oh, choose the minus root? Not very often, right? Usually they make you write the plus or minus, and then when you do problems, most of the time you're choosing the positive root. Here's an example where you choose the negative root, and the negative root gives us the right physics. So if we scroll up now, we can plot the velocity right next to the x displacement. So here is v of t versus t, and it starts off like this. Oh, sorry, I already messed up. It starts off like this, and then comes up and goes back down and comes up. And one period here is the same. It's still one period, and it's still 2 pi over omega. So the velocity and the displacement have the same period. That makes sense, right? And then the maximum velocity here, this is V max, that's the peak. But we start off with velocity 0 because we stretch it and we release it from rest. So for the position, for the displacement, we have the max displacement is A, right? And we have the max velocity is V max, but we can also write that as square root of K over M times A. So if square root of K over M is bigger than 1 times A, whoops. If square root of K over M is bigger than A, then this thing has larger peaks than the position x of t. So we have now displacement and velocity, which are both functions of time. Look at how far we've come in this class, right? We started all the way back. We were looking at real simple kinematic, stuff. And now we're doing dynamics with forces and things. And we have position and velocity, which are changing as, sines and cosines rather than just like, V equals AT, right? Where x equals, VT plus 1/2 AT squared. So now we've got sines and cosines in here. Which begs the question, what is the acceleration, right? How do we get the acceleration? The acceleration here in this problem is certainly not constant. Does anybody have any ideas of how we might figure out what the acceleration is? Let me clean up some space for us. Anybody have any idea as to how we might be able to figure out the acceleration? If you are in the 210 class, you already know the answer. If you're in the 205 class, though, you've got to come up with a non-calculus way of getting the answer. Right? So what do you think we could do? What kind of equations might tell us the connection between, you know, maybe the position or the velocity, the acceleration, the force, maybe from the energy, right? What are the things we've talked about today? We talked about force, talked about displacement, talked about velocity. Haven't talked about acceleration yet. That's what we're trying to get. We talked about energy. So think about that. Think about that. Anybody have any ideas? Let's just see some ideas in the chat. Don't worry about if your idea is correct or not, but let's hear some ideas here. You don't have to worry about being correct. Christine says F equals ma, and so we can plug in for the force, it looks like. So you've skipped a step there. Anybody else? Anybody have any other ideas? Well, I don't see anybody really discussing any ideas here in the chat. So does that mean you guys want me to give some hints, or does everybody agree with Christine, or what's the deal here? Hint, please. Hint, okay. So think about everything we've talked about today. So we talked about the force being minus kx, right? We talked about energy, right? Potential energy was 1/2 kx squared. We talked about v, right, as a function of x. 1 minus x squared over a squared. Then we said, well, okay, x as a function of t, we could write as a cosine omega t. And that allowed us to write v of t, which is minus v max sine omega t. Here, v max is square root of k over m times a. So now we've got x and v. We kind of want to find t now, right? Did I miss anything? Was there anything I talked about that I didn't remind you of? Yeah, we talked about energy. I kind of put that there as potential energy. Talked about period and frequency, and those are important, and those are kind of implicitly here. Those are kind of implicitly hidden in these quantities here. So the period and the frequency is there. But does anybody see how, like, can we connect the acceleration in any way to what we know from this? So does that help? Are any of these quantities right here related to acceleration? Are any of those quantities related to acceleration? And if they are related to acceleration, how are they related to the acceleration? I'm going to give you guys one more minute to think about it, and I hope that you are thinking about it, and maybe even if you're not making progress, that it's still good to exercise your brain, right? I'm going to give you one more minute, okay? Well, Kevin, you're in the 210 class, so you already know how to get the answer, right, from Calculus 1. So you can get the answer that way and just wait. Sometimes having calculus makes things easier. That is the lesson of this course. If you know calculus, everything is easier. Liliana, you can still kind of think about how to get there without calculus. Are you changing your answer, Christine? Because actually I would be very skeptical of doing v over t, because delta x over delta t doesn't work. So delta v over delta t wouldn't work unless you can take the limit as delta t goes to 0. Right. Well, I mean, there are a lot of, like, for example, in when we're doing kinematics, taking the limit is actually easy for a polynomial function because there's no delta t left over in the denominator. So there's really no limit to take. So you could pose it as a calculus problem, but then there's really no calculus there because you never actually have to take the limit. In this case, for sines and cosines, you would have to calculate the limit. Yeah. Okay, so it's been a minute. So let's go ahead and kind of recall. The way you get from acceleration to stuff we have over here is first remember that F equals ma, right? We always have Newton's second law whenever we're dealing with forces. So if we ever want to go from like force to acceleration or acceleration to force, we can always write F equals ma. But is there a way to write down the acceleration in terms of like the force? Well, we do actually know a little bit about the force here, right? We do know about the force. It's minus kx. So we can write minus kx equals ma. And if x is a function of t, then a is a function of t. Okay? The mass isn't a function of t. The spring constant isn't a function of t. So we have this expression here. So minus k over m x of t is equal to the acceleration a of t. Okay, so if we want to translate that now, over here. So it's minus k over m times a. Actually, there's one problem here that I see that actually no, this should be fine. Minus k over ma times cosine of omega t. Cosine omega t. Let me just fix up the arrows here. And now we have the acceleration as a function of time. When the cosine is 1, this quantity here tells us the maximum acceleration. And the cosine is 1 when you have max stretching, right? When x is a, you have maximum stretching. So a max is k over m times a. Okay? That completes our discussion of the simple harmonic oscillator theory in terms of like a mass on a spring. The next thing I would like to do is show that we can apply the same analysis to the simple pendulum. In other words, just a mass on the end of a string. Okay, give me a thumbs up if you're done copying that down so I can show how this same analysis we can actually apply to a completely different problem and get the correct results.
Professor, where did the negative go with the max acceleration? Is it?
I'm just taking the magnitude here, so it's yeah. So just like the V max has a minus sign in front, right?
Oh.
So I could rewrite it as minus A max.
I see.
A negative number, right? When the acceleration can be positive and it can be negative, the negative is not going to be the maximum, right?
Right.
The negative would be the minimum.
Yeah. Okay, thank you.
Okay, so let's go ahead now and do the analysis for a simple pendulum. Anybody still copying down? Everybody give me a thumbs up if you're done. Thumbs up if you're done. We got to kind of speed through the next little bit here. Liliana, Sammy, Kevin. Sammy, Kevin. We'll wait 30 seconds. Okay, I'm gonna clear it. It is in the book. It is in the book. So if you need to, go back, read the book again. Okay, now we want to look at a simple pendulum. So a pendulum is essentially a mass on a string that's been raised. It's allowed to hang down vertically, and we raise it up a little bit by an angle theta. Let's use red for the forces here. There's a force mg down on this pendulum, and there's a tension force Ft, which is along the direction of the string. The component of the gravitational force in this direction has to equal the tension force. Why? Well, this thing is not accelerating along the string, right? This thing is fixed with respect to the string. It's always, whatever the length of the string is, it's always that distance away from where the string is hanging, right? So the component of mg that's in the same direction as the tension perfectly cancels out with the tension. What about the component that is in the direction here? Well, that component there, you can check it yourself. If you analyze the angles here, you can show that this angle here is the same angle theta, and so that force there in pink is mg sine theta. I can draw a triangle here where the mass really goes along this dotted line path, and this triangle has sides L sine theta here, and L, oh sorry, I wasn't using a curly L, it's L sine theta, and L here. We don't care about the L cosine theta piece. The angle is theta. Now, what I'd like to do is assume that theta is small. When theta is small, sine theta is approximately equal to theta. Your book has a table of values comparing theta in radians with sine theta. Theta has to be measured in radians for this to be true. And you can really show this is true with some calculus, but here we kind of have to lean on a calculator a little bit and really kind of plug and chug some numbers to see that this is true. Maybe graphically we can see this is true by recognizing that this length here is the arc length on a circle. It's a portion of the circumference of a circle. We'll call it S. And S is equal to the radius times the angle in radians. And in this case, that's L times theta. And if theta is really small, then we're looking at a triangle which looks like this. So here's a small theta. And we can see that this distance here is approximately equal to, and let me make the brush size small here, that distance there is approximately equal to that curvy distance there. And the smaller theta is, the more those two are equal. So these are approximately equal. Okay. Okay, so what does that mean for the analysis here? Well, what it means is that the the force on this thing, which is there it is, I was looking for that, is mg sine theta. That means I can approximate the force as mg theta, right? I can approximate the force as mg theta. And if I approximate the force as mg theta, then obviously I'm approximating the arc length as well. So I also have to approximate the arc length s as L times theta. Okay, I have to do that. I'm forced to do that. If I say that theta is small and I make that approximation somewhere in my problem, I should also make that approximation everywhere in my problem where that applies, right? Well, theta here we can write as S over L, right? From this equation here. Well, then I can plug that in to this equation here, which leads me to the following equation. F equals mg S over L. Now notice one key feature of the pendulum. S, if I take S to be positive in this direction, if I take this direction here to be positive, then my force is negative. My force is in this direction, right? So again, we have a situation where the force is in the opposite direction as the displacement. So I should include a minus sign here. And if I include a minus sign, then I have an expression which looks a lot like what we just did. We have minus k and we have x. So we can instantly repeat all of the analysis we did before with k equal to mgl. So k equals mgl. Now the difference is, in order to make this true, we have to have the small angle approximation. So with small angle approximation, if we don't have small angle approximation, which means sine theta is approximately theta, then this is no longer true. So as long as we have a pendulum that oscillates back and forth with a small angle, we have this. This actually works really well. So that's why like grandfather clocks where the pendulum is swinging back and forth actually work, is because you have a really small angle, the arm of the clock is really long, and you get really good timekeeping. And this was actually the original way that time was actually kept in the past, was through using pendula. Pendula is the plural of pendulum. So it ends in A instead of So pendulum, pendulum, right, like this, and then pendula for plural, pendula. Okay, that'll be a test question, right? What's the plural of pendulum? I'm just kidding. Okay, so now we can just instantly repeat all of our analysis before. So what is the maximum displacement? What's the maximum displacement, which we called A before? Well, that's S now. That's S max. Well, we can just call it A again, right? We could just call that A. Or maybe what we could do is we could say, oh, wait a minute. That's L times theta, right? We could call it whatever we want, really. What really matters is the physics, right? So we can call this thing many different names, or we can call it just S max. And we can repeat the calculation for the period. If you remember, the period was 2 pi square root of m over k. Well, now this translates to the period of a pendulum being equal to 2 pi square root of m over mg over L, run through the algebra machine, and you get 2 pi square root of L over G. And so you can see that the period of the pendulum depends on the length of the pendulum. A longer pendulum means bigger period. And the gravitational acceleration. So if you design a pendulum clock on Earth, and then you take that clock to the moon, it's not going to keep time the same way because the gravitational acceleration will change. You'd have to adjust your pendulum if you're on another planet, right? Yeah, notice again, for a small angle, the period does not depend on the amplitude of the oscillations, as long as the oscillations are small. If the oscillations are not small for a pendulum, then you do not have, if the oscillations are not small, then the period will depend on the amplitude. I'll let you guys repeat the analysis. You can figure out what S is as a function of t, and the velocity as a function of t. Probably the velocity is the best one to take a look at. So before I let you guys go, Vmax. And by the way, we haven't covered all of the material in the chapter, but we've certainly covered the most challenging, the most mathematically involved material. So I leave you guys to kind of investigate the rest. And we'll definitely take a look actually at a lot of this stuff is going to show up in the next chapter when we talk about sound. Okay, so really take a look at those, the properties of waves in the next, the several sections that come after this stuff. But what did we have for Vmax? We had Vmax was square root of k over m times the amplitude. So how would we translate this? Well, k over m, so mg over L over m. So m's are going to cancel. And the amplitude is what we called S max, right? And this is going to be equal to square root of g over L. And then S max, again, we could write S max as something like L times theta, right? From this expression up here, L times theta. And we put theta max here. So we put theta max. Well, L is kind of like the radius of a circular motion. So maybe you could even change this formula up a little bit more, but I won't do that here. We're already over time. You can calculate the frequency. You can calculate the angular frequency. You can go and calculate the acceleration, the position as a function of theta or of omega t, as we did before. So I'll leave you guys with that there. And I'll allow you to ask any questions, but before you ask any questions, let us actually go ahead and stop the recording. So if you've got to go, then go ahead, leave, but I'll stick around to answer some questions.